Okay, here we are with lesson 9, changing course a little bit, and we're going to talk about examples of functions from geometry. So on your lesson worksheet you have some exploratory challenge exercises 1 through 4. You're going to complete exercises 1 through 4 on the lesson worksheet, and the first table you're going to fill in as you answered the questions to exercises 1 through 4. At the end of that, you will have a completed table which will be presented at the end, and continue the video to check your answers as you go. So as you are answering the questions, don't wait until the very end, check your answers as you're going along. So go ahead and pause the video and start on exercise 1. Okay, you're probably done with exercise 1, so let's check your answers. Again, if you are not sure about something, please make a note or highlight it and bring it to class so we can clear up any confusions you might have. Okay, continuing on, here is the end of exercise 1 and the beginning of exercise 2. Okay, continuing with exercise 2. And moving on to exercise 3. And finishing up exercise 3 and looking at exercise 4. And to finish up exercise 4, we come up with a formula that would fit for any square within a square when we're looking for a 1-inch border. So if you were using your table, if you're filling it out as you were going, you probably could have surmised the answers for exercise 4 based on the pattern that is created by the first 3 exercises, where you have the side length and you have a side length plus 2. If you square that side length and then square the expression side length plus 2, then because you are subtracting the bigger square or the smaller square from the bigger square, then that would result in this particular expression. So some things to think about. Think about a real-life situation that might require using the function we developed in exercise 4. Some examples may include the area of wood needed to make a 1-inch frame for a picture, the area required to make a sidewalk border, likely larger than 1 inch, around a park or playground, or the area of a planter around a tree. Alright, some things to discuss, and you can take whatever notes you need to in your journal. This discussion prepares us for the volume problems that we will be working on in the next 2 lessons. The goal is to remember the concept of volume using a rectangular prism, and then describe the volume in terms of a function. So recall the concept of volume. How do you describe the volume of a 3-dimensional figure? Give an example if necessary. Well, volume is a space that a 3-dimensional figure can occupy. The volume of a glass is the amount of liquid it can hold. In grade 6, you learned the formula to determine the volume of a rectangular prism. The volume, V, of a rectangular prism is a function of the edge lengths, the length, the width, and the height. That is, the function that allows us to determine the volume of a rectangular prism can be described by the following rule. V is equal to length times width times height, or volume is equal to length times width times height. Generally, we interpret volume in the following way. Fill the shell of a solid with water and pour water into a 3-dimensional figure, in this case a standard rectangular prism, Example, a prism with base side lengths of 1 as shown. So if we had the base as 1 by 1, keeping in mind that this would make, even though this doesn't look like a square, this would make a square, and then the height is going to be the volume. Then the volume of the shell of the solid is the height, V, of the water in the standard rectangular prism. Why is the volume V the height of the water? Well, the volume is equal to the height of the water because the area of the base is 1. Thus, whatever the height, V, is multiplied by 1 will be equal to V. If the height of the water in a standard rectangular prism is 16 7/10 feet, what is the volume of the shell of the solid? Well, the volume of the shell of the solid would be 16 7/10 feet cubed, because the height, 16 7/10 feet, multiplied by the area of the base, 1 foot squared, is 16 7/10 feet cubed. There are a few basic assumptions that we need to make when we discuss volume. Write these in your own words so that they make sense to you. A, the volume of a solid is always a number that is greater to or equal than 0. B, the volume of a unit cube, example, a rectangular prism whose edges all have a length of 1, is by definition 1 cubic unit. C, if two solids are identical, then their volumes are equal. D, if two solids have, at most, their boundaries in common, then their total volume can be calculated by adding the individual volumes together. These figures are sometimes referred to as composite solids. All right, here are some practices with volumes of rectangular prisms, solving them algebraically. Check your answers by continuing the video. So here's the answer to problem 5. Again, solving it algebraically is using the steps to isolate the variable. In this case, they used x. You can use whatever variable you want. And here's the answer to number 6. Okay. Next are some exploratory challenge exercises 7 through 10. Complete the exercises. Remember that base refers to the bottom of the rectangular prism. Check your answers by continuing the video. So here is the answer to number 7. Even though they do not show the work here, it is probably a good idea to show the steps to find the answer to these questions. Here is for 8 and 9. And for number 10. All right, let's wrap this up. We know how to write functions to determine area or volume of a figure. We know that we can add volumes together as long as they only touch at one boundary. We know that identical solids will be equal in volume. We were reminded of the volume formula for a rectangular prism, and we used the formula to determine the volume of rectangular prisms. All right, see you in class.